And our next speaker is Dominik Rothenhaeusler. He actually spent 1 year as a postdoc in Berkeley because the people in Zurich suggested that this is a good idea to do so. So he followed our advice, and he's now at Stanford University, and he talks about calibrated inference. The floor is yours.
All right. Yeah. Thank you so much for, can you hear me? Well, okay. Yeah, thank you so much for the invitation and the opportunity to speak here. Yeah, so this is a joint work with Yujin. She's a graduate student at Stanford and has done a fantastic job here. Yeah, before I start, yeah, thank you, Peter. You probably, most of you know this location. I have not personally worked together with Peter, but we spend a lot of time. Yeah, he was very generous with his time. I got a lot of feedback on my ideas, and yeah, he taught me a lot. So thank you for being so generous here. Yeah, and a lot of the ideas that you will see here later are inspired by kind of the ideas that I got around Berkeley from discussions with Ben and Peter. All right. So what are we trying to do here? It starts with the question: so how can we actually draw trustworthy conclusions? And in statistics, I would say we have a bunch of answers to that. First of all, we want to have relevant data or high quality data. Well, your assumptions should be somewhat correct. Your p-values should be valid. You don't want to go on a fishing expedition and so on. And ideally, if you really want to trust a scientific result, you will have independent teams that can replicate it across, well, different teams in different locations can get to similar conclusions. At this point, we can ask, okay, are we missing something here? What else is there? There's this recent paper, or this recent commentary, I would say, in Nature, that I found was very well formulated, where they would say, okay, repeating experiments is not enough. And well, it's a short comment, but they have this picture here where, or here you have like this certain phenomenon, and then you have a bunch of scientists looking at it from different angles with different methods of investigation. So this is often called triangulation. And they say, well, okay, if you just try to repeat an experiment, that's not enough, because like if it's just repeating what people have done before, you might share similar biases or similar issues that might have been in the first study. So what they say is what you should do instead is you should make strategic use of multiple approaches to address one particular question. So not just one approach, not just one type of experiment, but multiple ways of dealing with a certain question. Of course, this is not a new idea. This has popped up many times in the literature. Here, another article by Friedman, where he talks about how John Snow was working on the cholera. And it's a very nice example. I won't go into too much detail, but Friedman said, like, what's really nice about this example is that he's bringing together many different lines of evidence. So not just one particular data set, not just one methodology, but like many different methodologies that come to the same conclusion. Okay, now if you want to do this across multiple data sets, of course, that's perfect, but maybe also a bit expensive. So the question is kind of, can we already make strategic use of multiple approaches just on one single data set? And again, there's some work in the literature here. Of course, you probably also know about Lemur's paper, where he was complaining that people often do make statistical decisions somewhat randomly. So here he says, like, sometimes I include certain observations, sometimes I exclude them, sometimes I choose the equation to be linear, sometimes I choose it to be nonlinear. So like there are a lot of design decisions that I can make as a statistician that might be reasonable. And he says, okay, the audience now withholds belief, rightfully so, until you can show that your inference is actually adequately insensitive to your choice of assumption. So if you change your assumptions a little bit, that things will not change up too much. Yeah, more recently, also here, Ben is in the audience, gives us the example of a biologist who has a lot of modeling choices. And often there might not be one particular principal approach just for one particular choice. So then you want that the conclusions that you make are somewhat stable across appropriate choices. Okay, and here some concrete suggestions would be change the way you pre-process the data, change the way you specify your regressions, change the model for the errors, and so on. Okay, so just talking about where we are so far. Now you can look at this and start asking, okay, well, how should we actually choose these multiple approaches? How should we aggregate this type of things? Like, how should we report this type of uncertainty? So the main issue is that we usually don't really have a clear statistical model for this. So until we have a clear statistical model, it's unclear how to do things optimally and what distinguishes a good stability analysis from a bad stability analysis. And from a mathematical perspective, the main challenge here is that each of your methods might be somewhat biased for whatever you want to study, and you don't really know the structure and strength of the biases. You don't really know whether they share similar biases or whether their biases are completely unrelated. So you don't really know kind of how to aggregate it, how to report it, and so on. Okay, any questions so far?
If I take the machine learning point of view, I don't care about this. I have a model, it gives predictions. I'll check it, how accurate they are. You know, I'm trying to, it's easy. Why do we need this? If the goal is prediction. Okay, because it's a scientific.
Well, if you care about whether, okay, so this is not particularly about prediction. This is mostly about parameter estimation. But it's if your things are somewhat stable and your distribution doesn't change and everything is exactly the same in your test sub as it is in training, then yeah, you probably don't need to worry about these kind of things. But like as soon as there are some changes, you probably need to worry about quantification of uncertainty and also about like distributional robustness and these kind of things. And that's also one reason why I think the machine learning community has a lot of research in these areas these days. But this will not. Like this, I don't think this talk will satisfy machine learners. This is for statisticians. All right. So yeah, high level, we want to have a model for what's happening here. So I'll come back to that whole making use of different approaches and now just talk about the model here. So what I want to formalize is the notion of distributional uncertainty. You can ask, okay, what does it mean? So the idea is here, similar to the robustness literature, there's a target distribution P0 that you want to make a statement about. So maybe that's the population of the United States. But then when you set up your data collection procedures, there are all kinds of like mistakes that creep in, right? So there might be certain contaminations of the data. There might be some confounding that you might not be able to control for some sampling bias. There might be batch effects. So all kinds of distribution shifts and changes between the population that you care about and the population that you actually sample from. Now in statistics, we have a ton of methods to deal with known structures. So for example, you can do reweighting if you know kind of how, like the type of bias that you got. But what we want to deal with now is what if you actually have unknown perturbation? So let's say you do your reweighting and say, okay, I hope I control for everything, but what if something is still wrong? How can you quantify kind of the unknown non-adversarial perturbations that you will not be able to deal with these fancy statistical techniques? And this is very high level, so I'll go into more detail now in a second. As a running example, let's just deal with linear regression. So we're interested in a linear regression parameter of the unperturbed distribution. But now you don't observe IID data from the distribution that you care about, but from a perturbed distribution, peak psi, and you get your estimator. And now you can decompose the uncertainty into two components. So this is your estimate. This is the thing that you want to estimate. You get an error due to sampling. That's what we usually try to quantify in statistical inference. And then there's also this error due to the distributional perturbation, right? And we're going to put a little bit more structure on that in a second. Okay, any questions so far? Okay, so without any additional structure here, you kind of lost, obviously, right? So you can look at how have people dealt with this in the past. And often what people do is they put a kind of a bound on this based on background knowledge. So for example, in causal inference, we have sensitivity analysis where you say like, oh, I think my confounder is at most this strong. So then you derive bounds on that thing, and then you can integrate that. Or yeah, in the robustness literature, maybe you know kind of like which percentage of your population can be contaminated. And then again, you can actually design estimators here for which you can bound this error here. But that is somewhat adversarial, right? You look at worst case bounds. So what we want to do now is instead we just say like, okay, maybe nature is not adversarial and will not mess with us like in a worst case way, in which case maybe the distributional perturbations here are just random. Maybe this error here, maybe the difference between those two things is just random somehow, right? Okay, how can we deal with this? Any questions so far? Alrighty, so what are we trying to do? We want to construct a confidence interval that covers the unperturbed parameter. And as I said before, sensitivity analysis and other procedures, they often rely on a user knowledge. So you need to input how far you think those two things are. We will not do that. We will try to get it through a different version. We will connect it to the idea before where you say like, okay, you have multiple estimation strategies for one particular thing that you're interested in. And we're going to use that to estimate the strength of the perturbations on a very high level. I'll make that more precise in a second. Related literature, I already mentioned most of that, so I'll skip that. Just saying like the classic robustness literature and modern robustness literature is related to this, but they usually look at worst case bounds. In causal inference, people often look at differently specified regressions. Yeah, as I said, for example, lemur has been recommended in this, BNU, of course, also. Okay, so if we want to do the math here, first we have to choose an asymptotic regime, right? So of course you can choose an asymptotic regime where this is larger than this, in which case you can just ignore this and do statistical inference as usual. What we did was we chose a regime where those two things are of the same order. The reason for that is that we want to design our uncertainty measure to be an extension of current practice, and current practice, then of course you want this to be relevant. That's why we chose it kind of the same order. But of course, you could also say like, what happens? I want to do uncertainty quantification where this is large and this is small, but that's maybe a topic for another talk. Okay, so let's get to the meat here. So what is the most? I said we want to have the distributional perturbation somewhat random. So you can ask, okay, what is the most generic, most natural distributional perturbation that you can write down? Maybe you have your own answer to this, but for me at least, we said like, okay, what happens if I just take a particular event and I just randomly give it a slightly higher or slightly lower probability than in the original distribution, right? So math incoming. So in a very simple case here, I have a discrete distribution with weights 1 over m, and now I'm just drawing some random weights, psi case, and now each event gets randomly upweighted or downweighted compared to the population of interest. And then I draw from that perturbed distribution. And then if you do like a tiny bit of math, 2 or 3 lines, what you're going to see is if you look marginally at the variation, what you're going to get is the variance that you usually expect under IID sampling times a global scaling factor that depends on the strength of your distributional perturbation. So if there's no variance in your size, then this thing here will be 0. But as if you like amp this up, then marginally you will get a huge adjustment factor here. And the interesting thing here is that no matter which psi you choose here, you always get the same scaling factor. So this thing just blows up the variance of each empirical process that you look at by this scaling factor that depends on the unknown distributional perturbation that you don't know. Okay, any questions? Yes.
Don't you need psi to be differentiable or something?
No, just IID. Here at this point, I'm just looking at this discrete measures. This is not for continuous distributions. We have a similar version for continuous distributions in our paper. So psi can be anything. It should be like non-negative, and then you do this. Yeah. Okay, any other questions? Just to sum it up, what we did is we have a 2-stage sampling procedure. First, we mess up the distribution, like by randomly upweighting and downweighting events. And then marginally, when you look at the empirical processes, the variance is blown up by a constant factor that you don't know. Yes. You mean the expectation of psi? Oh, you could also take the expectation of this thing. The expectation of this inner thing is still 0. So you can show that like marginally your thing is still unbiased. Yeah, sorry, I should be more concrete here. So marginally this whole thing is still unbiased, but your variances are blown up by everything. So that is kind of a funny thing that happens here. So all the estimators that we used under IID sampling are still good estimators on this because you still have marginally unbiased estimators of the loss and so on. The only thing that will change is your uncertainty quantification. Does it make sense? Okay, so something that is actually slightly stronger here is we're going to assume that your data is so motivated by what we've just seen is that we assume that our data follows roughly a Gaussian distribution where you have the variance as usual, then times a scaling factor delta squared that you don't know. So this is a simplified version because of the particular asymptotic regime that we have to look at in our paper. You actually have to choose a triangular array of data sets to kind of make this statistically like super precise. But the way you can just think about it is like you just sample from a distribution and then you have a Gaussian distribution with a scaling factor here. And just like as a reminder here, if you forget all the story that I've told you so far, if you just draw IID from P0, this is standard statistical inference. It's just a special case here with delta equal 1, right? So you can just think about this as so far as just like, yeah, weakening the assumptions that we usually make with IID sampling. Yeah. I will come to that later when yes. Okay. Okay, so yeah, first question is when does this assumption hold? I already kind of gave you some little results. The distributional perturbation model here, you can actually show that you don't just get the variance is scaled by a factor, but actually that you still get asymptotic normality under the right scaling. There are a bunch of other kind of cases where you get the scaling factor in the variance. So for example, if you sample clusters of units where units in a cluster are like very close to each other, and the classes themselves are drawn independently and you don't know their membership, then you also get this unknown scaling factor in the variance that we just talked about. Okay. Now what we often get is people are like, okay, I could have written down something else and I would have gotten something and I would have gotten a different behavior. So we looked into that a little bit, and what you actually can show is on a symmetry assumption on your distributional perturbations, you will always get this global scaling factor delta. So the one that we just discussed before. And again, this is a little bit of math here. And the symmetry assumption here just states if two events have the same probability under the original distribution, then the perturbation strength that they will get will be the same. I'm not saying that they both get the same perturbation. I'm just saying that they exhibit the same perturbation strength. So what that kind of indicates here is a random perturbation. So you can't just take one particular event that has small probability and then make it suddenly have probability 1. That would be an adversarial perturbation, but you want random perturbations, and you can formalize it like that. Okay, yeah, and then you say like, so that's the main symmetry assumption. Then you can show that for all psi's, you will have this global scaling factor in the variance for empirical processes. Okay, you can also relate it to other statistical concepts. So for example, sampling bias or random confounding, you can show that we had that scaling factor delta. If your delta is very large and you write down a causal model, you will get a lot of confounding. If your delta is small, you will have little confounding. So the distributional perturbation model will mess things up and include like these issues that we often worry about in statistics separately. Okay, and just to show you like one little thing here, which is the violation of the IID assumptions. So if we draw from this two-stage model and the data is IID from the perturbed distribution, if you look at the marginal correlation, you will also get a global correlation between CDI and CDij, which will always be a constant delta squared. So somehow what the random perturbation model does is you can think about it as just creating observations that are marginally correlated. And they are all correlated with the same delta, no matter what transformations of the data you choose. Okay, any questions? Yes.
So how does sigma squared play a role in this result?
Oh yeah, sorry, that was an original. I wrote it first with covariances, and then you have sigma squared here. Yeah, sorry, that was just, I did not fix it yet. You can just delete that sentence. Any questions? All right, inference. Yeah, that is the interesting part now. First, how not to do inference. So if you use standard variance formulas, you will, of course, underestimate the uncertainty. Because of the fact that you will only kind of cover the perturbed parameter and not the original parameter. You can make that precise with math, but I don't have enough time, so I'll move on that. So and you can actually show that it's impossible without additional assumptions to get to the delta. So what we're going to do now is we're going to put down additional assumptions. Now we're coming back to the original idea that you don't just have one estimator, but you have multiple estimation strategies. So yeah, you have a bunch of estimators, hat theta k, that you believe estimate a very similar quantity. And the first assumption that we need to put down is that they're asymptotically linear. That is usually relatively easy to prove for M estimators under IID sampling. Under our two-stage assumption, you have to show that again, and we have some arguments in our paper why this thing here is still relatively simple in low-dimensional scenarios. The more crucial assumption is what Peter mentioned earlier, is that you now have a bunch of estimators here, and we're going to assume that all of these estimators, if you had infinite data from the unperturbed distribution, that those would actually all estimate the same thing. So you need some scientific background knowledge to not just come up with one estimator, but potentially 2, 3, 4, 5 different estimators that, if you had infinite data from the unperturbed distribution, estimate the right thing. We are robust if you don't, if that assumption is not true, but I'll come to that later. Okay, any questions so far? They're all estimated on one data set. But what you want is, like, in theory, if you had infinite data from the unperturbed distribution, that they would all agree. So there's like, yeah, one average treatment effect, and you have a bunch of different ways to estimate it, for example. Yeah, and one example that we often have in mind is that in causal inference, maybe you have not just one adjustment set that you can use in observational data, but you have a bunch of different adjustment sets that each equally make sense to you. So you immediately have not just one estimator, but like 5 or maybe 7. Okay, so how do we actually do inference? I'll go through that relatively quickly because I don't have that much time. So what you do is you look at the difference between two estimators, you square it. And now if you look at our asymptotic thing, you're going to see like, oh, this is now Gaussian distributed. If you take it to the square, you actually get a chi-squared distributed random variable with the variance of the differences of the influence functions times the scaling factor delta squared. So what you can do now is you can try to estimate this, and then you'll get a very noisy estimate of delta squared. You do that for a bunch of estimation strategies. And you do that for a bunch of estimation strategies, and then you can form an estimate of the perturbation strength by looking at the between estimator variation divided by the expected variation, assuming IID sampling. Okay, very high level. So one thing that is important here to note is it's not just about the between estimator variation, it is about the relative stability. It's not about absolute stability, it's about relative stability. And one reason why this makes sense intuitively is there's this quote by Wittgenstein, a philosopher, telling the story of someone who says like, oh, I bought several copies of a newspaper to assure myself that whatever was written in the newspaper is true. If you use 10 times a very similar estimator, that is not an indication that your result is trustworthy. So it's not the absolute stability, the absolute estimator variation that counts, it's the relative variation that counts compared to how different you expect them to be. So that's an important lesson here. Okay, yeah, and then like with some theory, you can build what we call Yujin intervals. Yujin was the student who worked on this. Things work as usual. You have your estimate theta, you have your normal quantiles, your variance estimate as usual, but now you have this adjustment factor delta hat that you need to like blow up your confidence intervals for the distributional uncertainty. And the probability here now is over both the sampling uncertainty and the distributional uncertainty. So what you're really covering here is the parameter that you want to cover and not the perturbed parameter. Okay. Any questions? Yes.
So how strong is the assumption of weakly correlated estimators? For example, I use M estimator with different loss function, would that count?
What you can do then in a pre-processing step is you can decorrelate them. We describe it in our paper, so you can do a linear transformation of your estimators to kind of again form independent ones. But if they're extremely highly correlated, then your estimate of delta hat will be very unstable, and you'll see that. And that is probably an indication that you should go back to your scientific knowledge and think whether you can come up with estimation strategies that are less correlated than the ones that you currently look at. Yeah.
But yes, following up on this, is this covered in your assumptions 1, 2, and 3? I mean, you assume implicitly that they're sufficiently different, right? Otherwise.
Yes. So if all of them have the same, exactly the same influence function, then you're screwed. Then you can't estimate delta. But as long as they have different influence functions asymptotically, you can do things.
So you need an assumption 4 somehow, right? I think you have not.
Yes.
So it's
yes. There's a part that.
I mean, it's,
yes, I need those 5Ks to at least be different. Yeah, there's a third part. Yeah, but as soon as you have.
yeah.
Okay. Any other questions? Yes.
Maybe it's way beyond, but you assume essentially parametric setting or a low-dimensional setting, right? So what happens in a non-parametric or high-dimensional setting?
So I think a similar thing still goes through for, let's say, the disparsified lasso and so on. But once you're just dealing with something like with L1 consistent estimation high-dimensional setting, I don't have anything for that. So you need to be in a semi-parametric setting. Net rates, that's what we got with you. Okay, how much time do you actually have?
8 more minutes.
10 minutes. Okay, so let me just quickly go through a numerical example here. So we draw from this causal graph. You want to estimate the causal effect of x1 on y. Now we have both sampling and distributional uncertainty here. Now, if you believe that this graph is true, you find a bunch of estimators. There's not just one. There's like 3 or 4. No, probably 6 or 7. And now, first, what we tried to estimate was delta, and we looked at 2 different things. First, when all your estimators actually estimate the correct thing, in which case you get a pretty good estimate of the underlying delta. But there's a lot of you get more conservative if one of your adjustment sets is actually wrong. So we added one estimate where you actually forget to adjust for a confounding variable just to see like how our method performs. And like theoretically, you can show that you usually get over coverage, and that's also what happens here in the simulation. So now here the red the red dots here are kind of coverage with confidence intervals that are computed as usual, and then the green dots are our kind of adjusted ones. And what you see is that coverage is much closer to 0.95, what you're actually interested in here. So here the takeaway is obviously that if you don't calibrate your confidence intervals, then you get under coverage because you will not estimate the distributional uncertainty. Okay, I'll skip this part and go to a bunch of high-level remarks here. So yes, what we sometimes get is that people say, like, okay, well, this makes very strong assumptions. And we agree, these are strong assumptions that you assume that nature is not adversarial and just randomly messes with your distribution, right? But also it is weaker than just assuming that the data is IID and just running with that, right? So in some way, we're just weakening kind of what is usually done in the most common inferential strategy in statistics. You can also generalize it that the perturbation that acts on X is different than the perturbation that acts on the epsilon. So you can do a component-wise distributional uncertainty model, but I'll skip the details for that. What we often get from practitioners is that they say like, oh, okay, I'm scared that my confidence intervals will blow up and just be like super large. And yeah, obviously you don't want that. In our application, it was actually reasonable. So sometimes we get confidence intervals that are twice as large. Sometimes we get confidence intervals that are similarly large. So at least in the application that we looked at, it was not completely unreasonable in terms of the final confidence intervals that we got. And of course, but still theoretically, it can happen that these confidence intervals will be quite large. And well, maybe if your assumptions are actually correct, then that just is an indication that the distributional uncertainty is of higher order than the sampling uncertainty. So what that means in some sense is maybe that the standard statistical confidence interval is actually not very meaningful because another type of uncertainty is of higher order than what we just computed, right? So maybe that is also a good warning that you're just like, okay, that you have to step back and say, okay, are my standard confidence intervals actually something meaningful here? Gonna skip that. Also gonna skip the looking ahead. I just wanted to say that we have a package for getting started. What was important to us, because I think it is not entirely clear directly how do you actually sample from a distributional uncertainty model. So we wanted to create a package where it's as simple as an R just running these two lines to get data. What you have to tell R is that the distributional uncertainty model will induce correlations between X and Y. So you need to tell R that both X and Y are drawn from the same perturbed distribution in some way. So the way we set it up here is we generate what we call a distributional seed. And the way it works, you just choose your sample size and also the distributional perturbation that you're aiming for. And so you get your distributional seed, and then you can just draw a Gaussian distribution and like draw from a multivariate the perturbed distributional uncertainty model. Yeah, and just to give you one example how this looks like. So both on the left and on the right-hand side, you see the QQ plot of 1,000 observations. Here, just like a standard Gaussian distribution, and here a perturbed distribution with delta equal 5. Uniform, random variable, and so on. So we also have functions for actually doing calibrated inference. We call it column for calibrated linear models. So you put in the formulas that you believe estimate the same thing. You put in the data, you put in your target, you get p-values and standard errors. Okay, so yeah, to just sum up the tool sets here, we have a bunch of, so you can just generate from the distributional uncertainty model, Gaussian distribution, uniform, binomial, chi-squared, and so on, what you usually would want to do. And we also have a bunch of kind of tools to do calibrated inference in linear models and calibrated inference in generalized linear models. Yeah, it's not very hard to implement. Each of those things you can do in a bunch of lines, but I believe it's easier to get started if those things are available. Okay, I have more philosophical remarks if I have time left. Okay, so what are we trying to do here? Yeah, so usually people think about statistics as dealing with sampling uncertainty. What we're trying to do is like extend the uncertainty notion here. And I try to make a case for, and more details in the paper, that under a distributional uncertainty model, you have certain types of confounding, you will have correlated data, and you will also have selection bias. So we're kind of extending kind of the uncertainty notion here a little bit. This is not an inclusion. So if your confounding is really adversarial, you should not use our method. right? Or if your selection bias is really adversarial, don't use our method. It's more like if you don't think nature is adversarial and more like random, then this is the right way, maybe, of thinking about it. Okay, one more philosophical comment here is, often in statistics, if n goes to infinity, we get uncertainty that goes to 0, right? So you might get confidence intervals with a length of 10 to the power of -4 and 10 to the power of -6. And you can think about this two ways. You first say like, oh, my uncertainty is almost 0. Or the other thing you ask like, am I actually measuring the right thing here? Am I actually capturing uncertainty here? So what happens in our model if n goes to infinity? You can show that if the estimators are uncorrelated, otherwise you have to do transformations, you can show that the overall variance estimate converges to a weighted between theta k's variance. So these are the theta k's if you had infinite data from the unperturbed distribution. If the assumption that I put down before is correct, then this thing here is 0, and your uncertainty estimate really goes to 0. Now, if for some reason, asymptotically, your estimators don't agree, then this will always be bounded away from 0, and your uncertainty estimate will never go to 0. So from a high level, I believe that makes sense, because what that just means, if your assumptions are almost correct, you will get very precise inference. So your variance estimate will go to 0. But if your assumptions are grossly violated, so if your things are actually estimating different things, you will have high uncertainty no matter how large n is. And in some way, kind of you can think about your assumptions as looking through a microscope. If your assumptions are bad, you will always have wide intervals. But if your assumptions are good, then your intervals will get smaller and smaller. Okay, any questions about this remark or anything else? All right. One last comment. Sorry to bother you here with the whole philosophical stuff. The reason that philosophy here, I believe, is a bit more important, or just these high-level thoughts, is that I don't think that constructing these type of uncertainty measures is really a mathematical problem. I think it's more of a design problem where you want to design something that is as intuitive and as close to kind of what people kind of like intuitively want to do, but also how they want to kind of the way they want to have the output close to something that they can interpret. So that's why I spend a lot of time on this, because I want to construct something that is very close and very intuitive to people. So we had this Chas's talk before where you ask like, what is the third number? So we somehow have this consensus in statistics that there is an estimate and then there's a standard error, and then kind of like the opinions diverge on kind of what we should report next, right? What is the next thing that we should report? And I can see at least like 3 versions of the future in 20 years, right? The first thing is that we just said, okay, maybe in 20 years, people will still do things the way they do them now. They'll compute the confidence intervals or p-values the same way for the most basic tools. Then there's maybe a more optimistic view where we say like, okay, there will be a lot of other numbers where we kind of issue such things such as like stability under distribution shift, sensitivity to outliers, method stability, and so on. So for all the kinds of things that can go wrong in statistical analysis, we'll have a bunch of other numbers. So people don't just look at those 2 numbers, but they look at a lot of other numbers. All right, and now there's this thing in between where you say like, okay, well, the other alternative is actually to try to integrate other types of uncertainty into our current variance estimate. So here the answer would be, we won't do a third number, but we will change the meaning of the second number and try to account for more than what people currently account for, if that makes sense as well. So I really hope that like we're going to do more, because I'm still a bit hesitant. We can capture everything in one number, but I also like binary decision making and the simplicity of just having one number. Yeah, that was the reason for doing this project. Okay, yeah, just to wrap up quickly, what did we do here? We built essentially theoretical guarantees for a version of a stability analysis that a lot of people already do or advocate for. What we get in the end are p-values and confidence intervals. So what I believe is relatively easy to interpret for people doing practical work. It's the output will be similar to what they're used to working with. As I mentioned briefly, it can expand it to more complex perturbations, so that the perturbations that act on your covariate space X might be different than the ones that act on the errors, for example. There are two issues that you might encounter in practice. So the first one is potentially large confidence intervals. We haven't seen that on our real world data set, but I could imagine that it happens. And as I said before, that could be an indication that your distributional uncertainty really is kind of higher order, or maybe your assumptions are completely off. And the other thing is it could be potentially be unstable, right? As I said before, 10 times the same newspaper will not help you here. So 10 times a very similar estimate might just lead to a very unstable estimate of delta. So this really encourages people to think hard. I hope it encourages people to think hard about how can they come up with different estimation strategies for their particular research question. Yeah, then that's it. Thank you for your attention. Papers on archive.
Thank you very much for the nice presentation. We already had quite a few questions, but I still give time for one or two. Vin?
Well, I'm very happy to see that a lot of our discussion now become mathematical types and you have formal results. So one comment I have on the absolute stability, I actually think that we also need absolute stability. The relative stability is really, the idea is already embedded all the test statistics like T and all of that, right? So that's, I think, corresponding to two numbers is both actually the absolute effect size and also the relative, which is the ratio of the two. But the two dimensions are both embedded in the absolute and also relative stability.
Yes, yeah, I agree. I like for us mathematically, that's what came out. I still think, yeah, you should probably also report the absolute thing. If you only report the absolute thing, I would just be worried that people are incentivized to just do like super tiny perturbations to their model and then claim that things are stable. So yeah, you probably need both to kind of really prevent people from, yeah, messing with things here.
Just a practical question about the in-between option.
Mm-hmm.
So now what my medical collaborators usually say is that all you do is you come in, you change what we've done, the errors get bigger. We lose results, right? You have to, and when you have so many options for what to incorporate, you could incorporate distributional assumptions, all these things. Mm-hmm. How will you actually convince them what are the things that they really have to account for? Because, from their point of view, we'll always add sources of uncertainties, and the errors will get bigger.
Great point. I've thought about this a lot. So the way we, so there are two things here actually. So the first one is the intervals might get bigger because now you account for distributional uncertainty. But also now you believe that those 5 models are correct, right? So you can do inverse variance weighting between them. You might still, and this is a tricky point, in standard statistical inference, you usually can't always do inverse variance weighting because you might actually test and see that those two things estimate different things. So inverse variance weighting will not be justified in a classical statistical setting. But in our setting, it is actually justified if you believe in a distributional uncertainty model. So our confidence intervals, if you do that on top of that, can actually get smaller also. And now what you report is now the average, a weighted average of all of your kind of estimation strategies, which I believe is maybe better things to do than just like randomly choosing one of them. And yeah, so there is an interesting aspect that you can actually get smaller confidence interval for that. So that was, yeah, that I knew that like if you always get larger confidence intervals, like people will just be like, no, sorry, I'm out of here. But yeah, so there is a way to actually be better at that. Yeah.
Okay, so in view of time, I think we close the session here. Let's thank both speakers again, Jess and Dominik. And